thank you so much for having me. I really like this talk, so I'm happy to be able to deliver it then. So as the title said, I did admin of Toad, and I think I learned a lot. So I'll just start it by just quickly going over what Advent of Toad is. So Advent of Toad is this yearly competition that started in 2015 with daily programming challenges, not language specific, they're very agnostic, just question, answer it, and you can do it basically however you want. It's 25 days, 2 questions each day. And we're now up with a lot of users. So a typical day will look something like this. You open up the day, you click the day when it opens, and you see this wall of text. So at the very beginning, you have this story. So this is some text that tries to have a little bit of fun, nothing to do with the question at all. So there will be every year a very, very small theme. So last year, 2021, there was a submarine theme. So we went on a submarine ride to save Christmas, and there's a little bit of that going on here. This was from 2020, so we had a slightly different theme. But this in and of itself is completely useless information for the problem at hand. Elsewhere, you actually have the problem. So it will describe what the input you receive is, how to read and interpret it, and what you need to get back. The input generally will be a text file, or maybe sometimes a couple of numbers. But it's something you can read in or download and read into your preferred programming language. And then lastly, you have a lot of times a section that has a work through example. So it will say, if the numbers are this, then you will get these answers. So you can see how the problem is. Where this becomes interesting, depending on how you're working through these problems, is you don't know beforehand what sections describe what. So here, there's a fairly simple case of it starts with story and then moves into question and worked example, but it is not always the case. You never know which parts are important. And we'll come back to why that's important later. So you have one question and you answer it. If you answer correctly, there will be a second part. And the second part will maybe be related to the first part. And you now have to calculate this second part, which tends to be harder than the first one. And if you're lucky, it's related to how you did the first time around. And you can save some time there. So here we have a very simple case of a very related part 2. So the first part was how many lantern fish do you have after 80 days? Second part is how many do you have after 256 days? So here it's very related. But depending on your solution, of the solution being your Toad, you wrote for part 1, it may or may not work for part 2. But where this becomes interesting is you never know what happens in part 2 before you do part 1. So if you're going for speed, you just write ahead with a fast solution that's easy to write, but it might not have been generalizable enough for you to handle part 2 well. So sometimes thinking a little bit at the beginning of part 1 can save you a lot of time in part 2, if you're lucky that day. So before that, I want to go back in time to far time, long time ago. It was the evening of December 1st, 2020. And well, it's technically the night before, because these problems start the second it turns December 1st on the East Coast. So I'm sitting there, I'm ready, nothing else to do. I decided this year I'm going to do adjunct code. I was also up ready. I'm waiting 5 minutes before, did some chill music in the background, opening up all the files, empty files, I'm ready. I watched the timer.
For, like, getting it done fast?
Yes, so so there is a couple of leaderboards. I'll get to that a little bit later too, but essentially some people go for speed to see how fast can you do. And there's a small leaderboard that will keep the first ones. So I'm sitting there, I'm ready. How fast can I do it? And at that end, and the problem was you did a list of numbers, 200 numbers, and a bit file, and you need to find the 2 entries that sum to 2020. I move along, have a lot of fun, write this wonderful solution. I started thinking a little bit on this one, thinking I might need to use this later. I wrapped it in a function. As you can see, we have a lovely 4-4 if return statement. As you can see, sometimes with speed, you don't need these curly brackets. Everything is about writing things fast. Later, yeah. So here, solution, it worked. I submitted, everything's going great. And oh no, the website doesn't work. And I'm not the only one. Apparently, we crashed the website. So having a website that had hundreds of daily users, suddenly that 50,000 users in 2 minutes, or maybe like in half a minute, crashed the AWS instance, and they had to completely tell it and spin up some better ones, which took a couple of minutes. And this was the moment I realized why I wanted to do this talk. I was sitting there thinking, what would part 2 be? I know it's going to be easy because we have a slow progression that the first couple of questions will be fairly easy. Most everybody can get through the top of first questions, and then they slowly get harder across the days, with the end ones both sometimes having like quite complex computer science structures and algorithms, but also just require a lot more code. So you have a progression going up. So I know that part 2 isn't necessarily a hard question, but I'm wondering what could it be? And this is why I realized there isn't one way to solving this. You can do so many amazing things. So there's a bunch of possible solutions. You can use loops the same way I used loops. And once you look at the leaderboard of the top performers, everybody uses loops, if and for, like if for statements, all the very, very simple thing, but it's just faster. You could make things using functional programming with like maps and everything like that. Generally easier to have loops. And for if statements, all of that, most solutions do better in Python, simply because, well, a lot of people write in Python. And every solution works well with that super low level structure. Another thing is all these solutions can run fast. If you find the right way of dealing with it, everything can be solved in seconds, even less than seconds. I found 1 year, someone wrote solutions to the whole year in C, and it ran in less than a second. So if you find the...
Not really.
I
don't agree.
I can get back to that later. Because a lot of these problems, if you have the right way of doing it, it can run fast. Another way to solve this specific problem is with expand grid. So we needed to find we can just find all the combinations, depending on which way the part 2 problem goes. Expand grid will work well, although depending on what we need to do, we have memory issues. We also just have fun with sample. You can easily just sample 2 observations and see how eventually you will find something to do it. Not necessarily a beautiful solution, but it might work. Well, it definitely will work. And while I was thinking about all of this, someone decided I want to code all of this up in RStudio. So to those of you that doesn't know, all of this problem that I just showed with finding numbers that sum to something can be written using this esoteric programming language called RStudio. That was the same as any other programming language, but instead of using more expressive syntax, it uses these keywords that makes everything sound like rock lyrics. So this is the exact same solution as the art code I showed earlier. And there's a whole different host of problems that you see in adjunct code. So there's these, as you can see before, which is simple questions, but we have some problems that reoccur year over year. We have the recursive problems. Every once in a while, you will get a question that if you can write a recursive solution, it's just going to be better. There's a good amount of problems that is what I like to call grid-based. So everything's being laid out in a grid of like X and Y, and like basically a big matrix, and you see values and you're trying to find out something in that. It could even be a maze. There was one year with a lot of maze-related problems, where what if you're a maze, how do you walk through it fastest, or how many different times, all the type of things. Another type of problems that I find that are handled really, really elegantly, if you're up for it, is what I like to call the parsable problems. So one year, it might have been last year, it was last year, we had this problem of we needed to find out where our submarine went, and we had this list of instructions. The instructions were like as follows: we have forward, down, and up with some amount. This is our input, and we need to figure out how far we went. And the easiest solution would be to do a for loop over everything, and then if else matching on F, D, and U to figure out what to do. But the more fun way of doing it is to first take this input and modify it, turn it into parsable art code. This mostly, in this case, subspaces with starting parentheses and slap on in parentheses. Suddenly we have parsable art code. We can define these 3 functions, forward, up, and down, set some variables to define the starting with our position of our submarine, and we can just run this code. And this just gives us the right solution. We don't have to do anything. This works in a surprising amount of, there's a lot of problems that can be handled this way. I'm not saying it's a good way to handle this problem, but it's a fun way of handling this problem. There's one time where I went a little further and redefined plus and minus because I felt it was easier to do it that way. And it's something we can fairly easily do in R. So we had a big string and just redefined what plus and minus does. And you can get a fairly beautiful solution out of it. Another type of problems, which comes up at least a couple of times every year, and sadly it surprises me every time, but it shouldn't, is my memory exhausted problems. So we have a problem from last year about lanternfish. So a lanternfish is a creature that is have a number denoted in how far away it is from reproducing. So here we are starting with 5 different lanternfish that each has a different amount of time until they reproduce. And after each day, all the numbers go down. If at any time a lanternfish is at 0, it will take its own number up to 6 and add another lanternfish at 8. And then we continue, and we slowly see our lanternfish population increase. So the first part of the problem was how many lanternfish would we have after 80 days? And the second part of this problem was how many would we have after 256 days? And if you're back here, you're thinking, I'm gonna follow the data structure that was laid out in the examples, make myself a vector and append on it, looping over everything. This will probably work well. And it works fairly well for part 1. It runs like in less than a second. Everybody's happy. So like you'd think, you're confident, I wrote something well. I'm just gonna change 80 to 256. It'll probably be fine. You run it and you realize that the very last vector would have needed to be allocated to a little bit more than 6.5 terabyte. And if this actually could run and you had done it naively, you would have needed to allocate 400 terabytes of data. You can do this without allocating that much. Like there is a better solution that allocates way less than a megabyte, but it didn't work if you did it before. So every year, a couple of times, and I should have known this when I read the question, because it's a low number, high number. And if you're not thinking carefully about this, it bites you and it takes forever. And I found my general workflow really separated into these like 3 steps. So the first step is we need to read in the data. The data in this problem is always this own format. And it's a text file that has stuff in it. And most of our general reading functions work fairly well. Or work well what they're doing, but this doesn't know CSVs or JSON files. So we have to write our own reading functions. And it really made me appreciate how I never have to write these functions myself. And we just have someone that worked hard on writing these functions, so I don't have to think about how to read in the data. Secondly, once you read in the data, which in this admin code can sometimes be half the battle, passing the data into a format you like to then do calculations. What you want to get your calculations into, like the format, really matters too. So we have like general things like vectors and matrices and data frames and lists. Environments to really be put in here too, but it mostly doesn't change for a lot of problems. But I would say that most problems can be solved using any of these. Almost any problem can be solved using matrices, data frames, or lists. But choosing the right format greatly enhances how you're able to solve the problem. Some things just work beautifully in a matrix that wouldn't work well in a data frame or a list. Likewise, being able to like infinitely nest things in a list, wonderful. It's something we can do in matrices. So you have its pros and cons, and knowing which format to put something in is highly beneficial. And then this here, we actually get the unit tests for free. We have a lot of the problems will come saying, oh, here, if you did input, it is output, and you can just test it with yourself. And lastly, get the solution. But most of the work really happens in 1 and 2. And especially if you have this own unknown input, spend a lot of time reading it in correctly, making sure it reads in correctly. So like, one of the things, if you join me later this year, you might learn a little bit something. There's a bunch of little threads that you will see. They are not particularly data science friendly. A lot of these are really tailored towards computer science. You can put things in data frames, but a lot of times it just doesn't work that well. And you'll be easier off using these simple control structures. But it's a time to learn about these little bit more data sciencey things. I ended up really loving repeat break. So repeat is just a for loop that never ends. And using that and then just having a statement somewhere that jumps out of it allows for much more flexible iteration, where you don't have to specify how long to run something for. There's also a bunch of different ways to play it. So, and I talked a little bit about it. We could go for just speed above all else. And that's fine. That is a very valid way of playing this. And it's a way that a lot of people do. Not too fast. Another way to do this is the shortest solution. So the shortest solution really is, and you might write it elegantly. Like we have readability from the chat, like writing, optimizing however you want. We can do, a lot of people try no dependencies, or you can like try specific dependencies. Some people try to put as much of the solutions in tidymodels, or you can do a whole different language. Some people use this as a learning opportunity to say, I want to learn Julia, I want to learn Python. So no one is forcing you to do anything. You can do all of it yourself, like do however you want yourself. I'm personally going for speed, and it's fun. It's what I find. That's the way I do it. But I still do readability second, because I write the solutions as fast as possible. It looks horrible, tidy it up, make it all look nice, and then tweet it out. And but as a humbling experience, you will never be as good as like the best of the best. Because we had start of last year, day one, David Robinson nearly topped the chart by getting both solutions of day one in less than 80 seconds, which is a truly incredible achievement, and never do it. Like, and just truly amazing. But like, while saying that, you want to go, you should go at your own pace. You can do, do whatever feels good for you. And then it's a weird problem, like it's a weird competition to be in, because it's December, typically one of the busiest time of the year. It can be hard to set aside hours to spend every evening or middle of the night, depending on where you're living, to work through these problems. I found that what a lot of people said is they give themselves a certain amount of time, and once they hit that time, they stop. So you can say, I'm working on this for half an hour, and if I can't do it, then I stop. And everybody can just do it at their own pace. With regard to leaderboards, we have a leaderboard on the site. The original leaderboard is impossible to get on because you're competing with everybody. And a lot of people are very fast. A lot of people are taking this very serious, streaming their attempts, but doing things incredibly fast. We can't beat it. And it only ever looks at the fastest 100 people for each part. So unless you're one of the fastest 100 people in the world, you don't need a single point. We added our own open R leaderboard that links up, does this point the same way, but heavily biases towards people that have the free time to answer, that do the solutions on time. Tan, wonderful man on Twitter, also added, it wrote his own leaderboard. So there's a small API from the website, and he wrote a leaderboard optimizing slightly differently. So instead of optimizing over time from opening to finish, it optimizes time between your first solution and your second solution. So this way you're not penalized by starting the next day. You're penalized by starting one day and doing part 2 later. But and you can still cheat. You can cheat this one. You can cheat by just looking at what the second part question is, do both at the same time, but it will very clearly show up on this leaderboard. So we have the different leaderboards for different things. And this is like where it becomes interesting. Like, the community is amazing. I spent a lot of time on Twitter on 1st December just tweeting at people, encouraging people, many private chats, Slack channels, people just going wild. Some people are live streaming their solutions, some are not. It's just an all-around great time. We're sharing solutions in Slack channels, learning from each other, finding different ways of handling the same problems. And there's so many different types of problems. So we have squares for 3 sides, which is a problem with your giving 3 numbers. Is it a triangle or not? Fairly simple problem. We have the encoding error, which gives you a list, and you need to find which number cannot be written as a sum of 2 of the 25 previous numbers. A little bit harder, slightly different type of problem. And then the very other end of the spectrum, see, it's at day 22. Basically building a turn-based RPG from scratch, and we need to find the optimal set of abilities for your character to do. So that is just so many lines of code to write all the logic of how you play, how they play, how all the numbers work out, and then creatively searching through the options to find the best. So that one, so many lines of code, you can't write it small because the sheer complexity of the problem statement is there, where you can probably write a one-liner for the first one if you read everything in neatly. And that's my other takeaway is all these problems are so clearly written. I always know exactly what they want me to do. I might not know how to do it, but I almost always know how to do it. So if you are working in dissertation and wanting to see how other people are getting about writing problems, I encourage you to look at how these problems are written, because they tend to work really well. And they have a small veneer of, oh, it's about elves and Christmas. But in reality, very quickly goes down to these completely unrelated scenarios. Slide right here. So my take home, and I'll, since we have some time, show some other links as well. So my take home for you is that if you want to join, you might learn a little something. There is so much power in the community. meet some friends, you can learn something, make memories for years. And most importantly, you might have fun. At the end of my talk, the 4 questions, if there's questions, I just want to show. So here we have like, I know code in its own thing. So you can see like here, say that day sets, we can see everything in here, and we just, the input right here is just some code, some structure right there. So all working through the same thing. We have some stats we can see. For each year, we can see how many people solved different ones. We see a lot of people do the first ones, not that many people do the last ones, partly because the last ones tend to be like just hard. But overall, the slope works. And people just drop out because it's a big time commitment. I also have the leaderboard for our art community. It works really well. We can search for people. I didn't do a lot, so if I'm in here, I'm ranked 33 here because I just didn't do as much. So I like stopped halfway through. And lastly, I also wrote a little bit. I put up a small little website themed appropriately with my solutions that I have so far. So if we go to the different days, you can see the solutions I wrote, and I also included how fast it took for the different ones to take. None of these are particularly written for speed. All of my solutions, even unoptimized, runs for, this one was a little bit longer. Oh, it's not written for speed, this one's written in, but most of it run. Like most of my solutions for this take less than a second. And with a good amount of optimizations, it could be a lot faster. And some of this is just isn't R-friendly code. Most every year there's a hashing problem, and hashing something a lot is not a fast thing to do now. But yeah, that's what I have. Any questions?